Alright, f of x is equal to secant, or not secant, cosecant x, and we get 2 cosecant 2. Alright, so what's f prime? Mad by that. Any chain rule here? Alright, now if I put f prime at 2, I'm going to get negative cosecant 2 cotangent 2. And I know it looks ugly, but it's better to use the exact value in that case. So my tangent, t of x, would be, alright, the slope, which is negative cosecant of 2 times the cotangent of 2 times x minus 2 plus f of c, which is the cosecant of 2. Alright, first off, is that okay? Just take the derivative and then just build the function based off of, remember this guy's your f prime at c, this is your c, this is your f of c. Alright, so let's go back to the calculator. I gotta redo the tangent here. So I'm gonna start here, delete everything. I'm going to get the negative cosecant of 2 times cotangent of 2, and then close that up. That's going to be times the variable minus 2 plus the cosecant of 2. That's my tangent, and I'm going to overwrite all that data and get those values. Now here I need to change that to the cosecant. The original function is the cosecant, so I'm doing the cosecant there. That'd be easier. Alright, so we got our answers. So, how's that approximation? The 1.9 is kind of far off, even though we're talking in the hundredths column. It's farther off in the hundredths column. Actually, it's farther off in the thousandths column. It's like 0.732, 0.00732 difference. So it's not that far off. At 0.99, it looks pretty spot on. At 0.2, it's spot on. 0.201, it's spot on-ish. And it starts to vary a little bit as you're getting a little bit farther away from that. Does that make sense? The biggest thing is building your tangent line. Once you're able to build your tangent line, the rest is just, alright, put them into a calculator, build the equations into that middle line right here, put in your values, and let the calculator do all the heavy lifting. If you take a look at like 2 here, and you see what's changing, that's the accurate one. That's the 100% accurate one. But look at the number that changes. It's the 5th number past the decimal point. So we're talking about tenths, hundredths, thousandths, 10,000ths. The 100,000ths place is the one that's changing. So that would tell me that these are pretty accurate approximations. And this is more proof that the closer you are to the number that the target is, and that number is 2, the linear approximation is going to be really, 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 really good. And the farther away you get, and 0.1, believe it or not, when you're dealing with the unit circle, 0.1 is a little bit farther down the road than you would think it is, than just 0.1 from a number, because it only goes from 0 to 2 pi, which is 6.28. So a 0.1 is a little bit more of a jump than it normally is. But we kind of see that happening here. The hundredths number is changing, and it's changing by a lot. Here, it's changing a lot farther down the road in the number. And here, they're pretty much identical, at least to this calculator's satisfaction. Here, it's changing pretty far down the road. Here, it's changing not so quite far down the road. And the farther you get away, if I went to 2.2, it's going to change a lot more, and it's going to change a lot closer to the decimal point. Make sense?